Wait for a few minutes, okay? Hello? Wait for a few minutes, 5 minutes. I'll be there.
Good morning, sir.
Begin. Hello? Good morning, everyone. Am I audible?
Yes, sir.
Good morning, sir.
Yes, sir.
So today we will start with the Hahn-Banach theorem. So let me give you some introduction about it. First. Okay. So far what we have done is we have seen bounded linear functionals, correct? Okay. So we have seen linear functionals, bounded linear functionals, And we have learned some properties of these. Okay, we have seen some examples, correct? But what we have not seen is, so we found some examples. We saw some examples, but we have not yet seen that whether about the existence of a linear functional, okay, on a non-linear space. So Hahn-Banach theorem gives this. It tells that there exists a linear functional on the space on non-linear space, and in fact, this the linear functional that that arises holds some properties. Okay, so what we do, so we start from a subspace, a one-dimensional subspace. Okay, so let X be a non-linear space, and so you all know so you all know that one-dimensional subspace of a linear space looks like span of
Straight line.
straight line means span of x naught. Okay, where x naught is non-zero, where x naught belongs to x and it is non-zero. So say if we are in a finite dimensional space, say in R2, then it is nothing but, so if this is x naught, then span of x naught is nothing but alpha x naught, where alpha belongs to the field. Alpha varies over field. So when we multiply this by 1, we will get 1. When we multiply it by 0, we will get 0. When we multiply it by minus 1, we will get this. Multiply it by half, we will get this point. So in fact, we will get this line. Correct? Any doubt? So a one-dimensional subspace. So span of x naught is a one-dimensional subspace of x. Okay. So as I said, we didn't say anything about existence of a linear functional on whole of x, but we can say about a linear functional on this subspace span of x naught. How? So we define a function f from span x naught to, say we are in K. How do we define this? So any element in span of x naught is of this form, correct? And we map this point alpha x naught to alpha. So it is clearly mentioned here, this alpha belongs to K. And in fact, this is bounded. X naught is linear and it is bounded. X naught is linear and bounded. So this means there exist linear functionals in a one-dimensional subspace of any non-linear space. So any doubt so far?
No, sir.
Okay. So with this, so what Hahn-Banach theorem does, uh, this theorem says about extensions of this functional f naught to whole of the space X. Okay. So this means Hahn-Banach theorem answers the following question. This question. So Hahn-Banach theorem answers this question that I am going to state here. So question is, if we have a non-linear space and say X naught is a subspace of X and G from X naught to K is a bounded linear functional, then question is, does there exist a bounded linear functional f from X to K? Okay. So I said this f will be extension of G. So what does it mean by extension? This means
Is the domain.
f, when we restrict it to X naught, we will get G. Okay. So this
Yes, sir.
means f of y equal to G of y, and this is true for all y in X naught.
G.
So if this happens, we say f is an extension of G. Hello?
Yes, sir.
Am I audible?
Yes,
Yes,
sir.
sir.
Okay. So we will answer this question affirmatively, and that is the Hahn-Banach theorem. And in fact, we will see something more than this extension. Okay. For answering this question, we need some terminology, and first one, you all already know this thing, partial order
Set.
partial order set. You all know what is a partially ordered set?
Sir.
Partially ordered set. Can anyone recall?
So if we have a set,
Okay.
let S.
रिफ्लेक्सिव होना चाहिए एंटी सिमेट्रिक और ट्रांजिटिव
हाँ, बहुत बढ़िया. तो मान लेते हैं ए हमारे पास कोई सेट है. Then
X Y Z belong कर रहा है हमारा A से.
okay, any set X Y Z belongs to A.
Then the first property is A related to A.
A related to A. So here this relation we will, so since this is called ordering, so ordering means we will use this for order. Okay, this is the relation.
For all A belongs to, for all X belongs to, sir X करना है हमें यहाँ पर तो. हमने X Y Z
X करना है, ठीक है.
X belongs to A. Second property हमारी है कि अगर X related to Y है,
X related to Y means X less than Y.
Y less than X, it will provide X is equal to Y.
And this implies X equal to Y.
That is the anti-symmetric property.
Okay.
Third one, if X is less than Y,
Okay.
Y is less than Z, this implies X is less than Z.
So this is, so first one is reflexive, second one is anti-symmetric, and third one is transitive. So if any set has this relation, this ordered relation that will denote by this less than equal to, if A has this ordered relation, then we call it is partially ordered. A is partially ordered. Okay? So what is chain?
If all elements of a set are comparable.
Okay, all element of that set. So as a set B of A is, so we have A is a partially ordered set and B is a subset of A. Then B is chain if every element of B are comparable. Means for all x, y in B, what we have, x is either x less than B or y less than x or both. Correct?
Yes, sir.
Okay. So then you also know what a John, what is the John? Okay, what is John's lemma? What is John's lemma? So do you know? Do you remember its statement?
So that we have a maximal element in upper bound.
Okay. So if we have a set which is non-empty and partially ordered, so A be partially ordered set, okay, and we have a assumption. Means what is the assumption? Assumption is suppose that every chain has an upper bound. This is the assumption. Then what is the conclusion? Tell me. Complete it.
That chain has
You have already seen this in algebra course, method theory course, and discrete
chain has maximal element.
mathematics. Complete this.
Then
Then
chain B has upper bound, then it has a maximal element.
then A has at least one maximal element. Okay.
Oh.
So we will be using John's lemma to prove the Hahn-Banach theorem. So let me give you an exercise, easy exercise. So exercise is every space which is non-zero has a basis.
Linear algebra में किया था.
And we call it ML basis. You already know this, okay? ये आपने पहले किया होगा. यहाँ पर एक क्वेश्चन है मेरा. Since I have written here x non-zero, okay? So you all know this is a vector space. This is a vector space, correct? Am I right?
Yes, sir.
This is a vector space over R or over any field K. Am I right? नहीं होता क्या ये वेक्टर स्पेस नहीं है?
सर
हाँ.
वॉइस कभी इको आ जा रहा है, कभी बहुत स्लो हो जा रहा है, थोड़ा सा सर इसको क्लियर कर दीजिए.
इसको मैं कैसे क्लियर करूँ?
ये सर ब्रेक्स
हाँ सर, सबके साथ हो रहा है, मेरे साथ भी यही घटित हो रहा है।
सर आवाज
मैंने सर आपको लिखा भी है चैट बॉक्स में काफी देर पहले।
कभी स्लो आती, कभी तेज आती, कभी गूंजने लगती है।
इसको मैं कैसे सही करूँ बताइए? ये नेटवर्क प्रॉब्लम तो मैं नहीं सही कर
ऑडियो
सकता।
वीडियो में जाकर के और हम उसको सेटिंग पे जाके ऑडियो वीडियो पे जाके बैकग्राउंड नॉइज करके उस पे शायद हो जाए अगर आप करें तो।
अभी ठीक है?
यस सर,
पहले से ठीक है?
यस सर,
Okay. So is zero a vector space? Is this set
Yes, sir.
a vector space?
Yes, sir. Yes, sir.
And what basis? Okay. So what is its basis? Anyone?
इम्पटी होगी सर।
Okay, empty set. Empty set is the basis of the zero-dimensional vector space. Okay. So let's move ahead. Now we will state the Hahn-Banach theorem. Before stating that, we need another notion that is called sublinear functional. You have seen one example of sublinear functional. Let's see the definition first. What is a sublinear functional? So suppose we have a linear space, X a linear space. Okay. Over K over, say we will be doing in R. So here I am saying R. Let me say K. K could be R or C. Okay. A mapping map F from X to K is called sublinear. So it is called sublinear if number one, this happens. Okay, and this is true for all x, y in X. Second is homogeneity. This is true for all x in X, and alpha positive and alpha belongs to K. So we should write this. If we are in C, then it will be mod of alpha. If so, here I should write K in L. Correct? Any doubt?
The linear sublinear में कोई difference?
हाँ, this is sublinear. Linear मतलब लीनियर होता है जब f x plus y is equal to fx plus f. This is called linear. Okay, and since there is this inequality, it is called sublinear. So do you know any example of a sublinear functional? You all know one such example. So if x is a non-linear space, then you define norms on x. Okay, so I was wrong here. I was wrong here. So let's do it. So we are taking x to r, and
Why?
okay. So here, so you know norm of alpha, norm of x plus y is less than equal to norm x plus norm y. Correct? Hello?
Yes, sir.
Is it right? So this comes from triangle inequality. And you know alpha of x is mod alpha norm x. And this is true for all x in x, alpha in x. So this means norm is a sublinear function. Correct?
Yeah.
Okay. So now let us state the main theorem. Main theorem, by main theorem I mean the Hahn-Banach theorem. So this is extension of linear functional. So let's state this. It states that let X be a real vector space. So what does it mean by real vector space? It means X is a vector space over the field R. Correct?
Yes, sir.
And P is, sorry, not PB. PB sublinear functional. Sublinear functional on X. Okay, so now we take a linear functional on a subspace of X. Let F be a linear functional on a subspace of X. It satisfies this property. So fx is always less than or equal to px for all x in z. So as I said, Hahn-Banach theorem is an extension theorem. Then there exists a linear functional f tilde on x such that f tilde m equal to f tilde of y equal to fy for all y in z. Okay, so I'm writing z like this. Z. Oh, why am I writing m? So it is z. F tilde restricted to z equal to f, that is f tilde y equal to fy for all z in y, and f tilde x less than equal to px for all x in z. Okay. So this is the Hahn-Banach theorem. Let's see it for a minute and understand this. What does it say? So read this statement and understand.
Not yet.
Oh, sorry. क्या हुआ? Okay. Okay. Let's move ahead. So let's see how this theorem answers our question. Okay. So here we had x a non-linear space, and x naught is a subspace, and we had a bounded linear functional. So question was, does there exist a bounded linear functional on whole of x which extend g? Okay. So if you see, we have a linear functional f
F.
on subspace z, then we are getting an extension of f, but
On.
in addition it preserves something. So this f was subordinated by p, means f was always less than equal to p, and this f tilde was always less than equal to p. Correct? So this is the Hahn-Banach theorem for vector spaces. So we will see Hahn-Banach theorem for non-linear spaces. So where there the extended function the extension functional that will preserve norm as well. Okay. So its proof of this theorem is lengthy, so we will divide the proof in various parts. Proof. So before that, any question, any doubt? Hello? Hello?
Yes, sir.
Am I audible?
Yes, sir.
Any doubt? So जो मैंने नोट्स आपको दिए हैं वहां पर कुछ टाइपोज हो सकते हैं, ठीक है?
M की टाइपो है Z वाली एक्सटेंशन के टाइम पे.
हाँ, तो वो उसको आप ठीक कर लीजिएगा.
ओके सर.
ओके देन कोई डाउट है तो पूछिए.
डाउट नहीं है, एडजस्ट कि हम क्यों एक्सटेंशन के लिए देख रहे हैं, मतलब
हाँ?
इससे हमें क्या, जो हम एक्सटेंशन ढूंढ रहे हैं लीनियर फंक्शनल का,
हाँ?
जो मतलब Hahn-Banach थ्योरम है, वो क्यों मतलब
क्यों ढूंढ रहे हैं? आपने ये पूछा तो क्यों ढूंढ रहे हैं ना? हमने ये लेक्चर जब शुरू किया था, हम एक मैंने कुछ बोला
एग्जिस्टेंस
था एक्जिस्टेंस के लिए, ठीक है? हमने कुछ एग्जांपल्स देखे, लेकिन हमने केवल एग्जांपल दे दिया, हमें मालूम नहीं था कि ऐसा एग्जिस्ट करेगा. हमने एक एग्जांपल दिया और वो लकीली लीनियर फंक्शनल बन गया, ठीक है। क्वेश्चन था कि क्या हमने एग्जिस्टेंस के ऊपर तो बात ही नहीं करी थी कि एग्जिस्ट करेगा या नहीं करेगा।
तो
Correct?
सर अगर हमने एक्सटेंशन ढूंढ लिया तो उससे एग्जिस्टेंस का क्या लेना देना है? लाइक हम कैसे हमें पता चल रहा है कि एग्जिस्ट कर रहा है नहीं कर रहा है अभी भी,
हाँ,
अगर हमें
वही
एक्सटेंशन मिल गया?
वही बता रहा हूँ कैसे कर रहे हैं। देखो, मैंने ये जब शुरुआत करी थी तो मैंने एक सब स्पेस लिया था, वन डायमेंशनल सब स्पेस,
यस सर।
वहां पर एग्जिस्ट करता है लीनियर फंक्शनल, एक वन डायमेंशनल सब स्पेस में एग्जिस्ट करता है, वो मैंने आपको दिखाया यहाँ पर, ठीक है।
यस सर।
है ना, ये एक लीनियर फंक्शनल था जो कि बाउंडेड भी है नॉन लीनियर स्पेस में, करेक्ट।
यस सर।
अब हमें मालूम है कि वन डायमेंशनल सब स्पेस में लीनियर फंक्शनल है, हम देखना चाहते हैं कि क्या हम, अगर हम कहें कि इसको मैं एक्सटेंड कर पाऊंगा पूरे एक्स में, होल एक्स में, तो मैं कह सकता हूँ कि एग्जिस्ट करता है ना।
सर।
तो वही हम देख रहे हैं अब इस ये एक सब स्पेस में था, छोटे से सब स्पेस में, अब इसको पूरे नॉन लीनियर स्पेस में, और यहाँ पर अभी हम केवल वेक्टर स्पेस की बात कर रहे हैं, बाद में हम नॉन लीनियर स्पेस के लिए अलग से थ्योरम देखेंगे, जहाँ
ओके सर।
ठीक है, एक सब स्पेस में हमें एक फंक्शनल गिवन था, हमने उसको एक्सटेंड कर दिया पूरे स्पेस में, ठीक है।
यस सर।
तो इससे आपको एग्जिस्टेंस पता चली कि हमें वन डायमेंशन में तो मालूम था ही, हम उसको वन डायमेंशनल स्पेस में, अब मान लो वो बड़ा हमारे पास n डायमेंशनल वेक्टर स्पेस है, तो हम वहां पर भी एक फंक्शनल मिल जाएगा, एक्सटेंड कर पाएंगे उसको, ठीक है।
सर।
ओके, सो फॉर प्रूविंग दिस वी विल यूज जॉन्स लेमा, ओके। सो हम क्या करेंगे, हमें हमें जो गिवन है पहला जो पार्ट है उसमें क्या होगा, तो इन फर्स्ट पार्ट, so we are given f which is from z to r, this is linear functional। अब हम इसके सारे एक्सटेंशंस देखेंगे, ओके। एक्सटेंशंस मींस, so what we see, we will define g, अब g जो है उसका कोई एक डोमेन होगा, जब मैं बोलूंगा एक्सटेंशन देखेंगे, इसका मीनिंग है तो dg contains z, correct, and g, when we restrict g on z, we get f, so we see all the extensions, so g extension देखेंगे of f, and we'll define a partial order relation on the set of all extensions of f, okay. So
Yes.
then what we do, we will use John's lemma, हम देखेंगे कि सारे चेन का अपर बाउंड है, ठीक है, और बाय जॉन्स लेमा हमको मिलेगा कि एक मैक्सिमल एलिमेंट होगा, और वो मैक्सिमल एलिमेंट को हम एफ टिल्डा से रिप्रेजेंट करेंगे जो कि लीनियर फंक्शनल होगा, ठीक है। so let's do that, so this is our first part। सेकंड पार्ट में हम देखेंगे कि जो 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 मैक्सिमल एलिमेंट हमें फर्स्ट पार्ट में मिला था, ए में जो मिला था जॉन्स लेमा की मदद से, वो एफ टिल्डा पूरे के पूरे एक्स में डिफाइंड है, वो लीनियर फंक्शनल है ऑन होल एक्स, करेक्ट, ओके। तो आई विल बिगिन विद ए, तो आज हम ये कंप्लीट नहीं हो पाएगा, कहाँ तक है देखते, कहाँ तक कर पाएगा, ठीक है, ओके।
Yes, sir.
So let's begin. So first we define a set E. What is the set E? E is the set of all extensions of F. This means G is a linear functional on its domain. Okay, so where DG is a subspace of X. And it contains Z. Okay, so this is the condition on DG. And what is the condition on G? I said G is extension of F. This means G, when we restrict on Z, we get F. And there is one more relation. So what is that relation? We have to
X is less than
we have to
subordination.
take care of this thing also. So and one more thing is there. G of X is less than equal to P of X. And this is true for all X in the G. So this is our set E. So this means E is set of all extensions of F which satisfies this relation. Gx is less than equal to Px. So I said we will use John's lemma. So let's see what is John's lemma. John's lemma says that we have a non-empty subset, non-empty set, and it is partially ordered. So this means first we have to see whether E is empty, non-empty. E is non-empty. Why? Because F belongs to E. Any doubt here? See, F is
Yes,
from
sir.
Z R. Z is subset of Z, correct? Every set is subset of itself. F restricted to Z is X, and Fx less than equal to Px. So these three things hold. This hold, and this hold for F. So this means F belongs to E. Correct? Hello?
Yes, sir.
Is it correct? Do you
Yes, sir.
understand this? So now we define an an ordering, which makes E partially ordered set. Now define an ordering on E. So we define a partial order relation on E as follows. So what we do, we take 2 points, 2 members of H, E, G and H, and we say G is less than equal to H if and only if number first. So it is intuitive, it is clear, it is natural that
Contain DH.
so number one thing, DG should be subset of H and H restrict it to DG, we get G. So, in other words, H is an extension of
G.
G. Correct? So this is reflecting G to C. Take this is always true. G less than equal to G. Because DG is the subset.
DG.
Okay.
G restriction on DG is equal to G.
Huh? G restricted to DG equal to G. That is the definition of G. And G is antisymmetric. This is also true.
Yes,
G
sir.
is less than equal to H. And H is less than G.
G
So
is equal
from
to
this, DG contained in DH. From this,
H containing
contained in DG. And from these two, DG
both
equal
are
to
equal.
DH. Now it is easy to see. Okay. That transiting less than equal to H, H less than equal to K. So this means DG subset of DH and DH subset of
Subset of
DK.
D.
So this means
So
DG subset of DK. Okay.
sir.
Any doubt?
No, sir.
Implies DG subset of DK.
तुम्हें क्यों दिखा रहे हैं?
And one more thing from here, when we restrict H, when we restrict K on DH, we'll get H. And when we restrict H on DG, we'll get G. This means when we restrict K on DG, we will get G. So this is transitivity. So this implies is a partial ordered relation. So E is partially ordered. E is and E is non-empty, partially ordered set. Correct?
Yes,
now,
sir.
Now there is another assumption in the John's lemma. It was every chain has a upper bound. Okay, if every chain has an upper bound, then the set will have a maximal element. So now choose a chain in an arbitrary chain C in E. Okay, so chain in E for any chain. So this is chain in E. We now define G theta, G head. Define G head. G head from, okay, what is DG head? We will define what is DG head. Okay, G head to R such that G head, when we restrict to DG, we will get G. And now let's see what is DG head. DG head is union of all F, don't write F, say write H in C DH. Okay. Here G belongs to C. Sorry. G belongs to the chain C. Okay. So you all know So since C is a chain, any two members are comparable. So if we have G, H, K, so this is for example, okay, this is for example. Suppose we have a chain, we have chain with these three elements, okay. So you know G and H are comparable, H and K are comparable, K and G is also comparable by definition of chain.
Yes, sir.
Correct? So this means, so from say this is the relation between G, H and K. So this means DG will be subset of DH, DH will be subset of DK. Correct? So this is only for, this is an example. Okay. So here in this we took a chain and we are taking union of all domains, all
Domain.
subspaces DH. But you know, if H1 and H2 belong to C, then one of these two hold.
Content, हाँ.
Either this or DH2 contained in DH1. One of these two holds. One of these two. Correct? Correct? If H1 and H2 are equal, then they are equal. Means in that case both happen. Any doubt here?
No, sir.
Okay. So this, and you know all DH1, DH2, all these are subspaces. Correct? These are subspaces. So this means union G in C, DG will be subspace. This is a vector space. Here you know from your vector space theory that if A is a vector space or A is a subspace, B is a subspace, then A union B cannot be a subspace. Do you know this? It need not be a subspace.
Not to be, हाँ.
Need not to be a subspace. For example, so this is a subspace. This is a subspace. That is a subspace. Union is not subspace. Do you know this? You know this?
Yes, sir.
लेकिन हम यहाँ पर कह रहे हैं कि ये यूनियन सब स्पेस होगा, वेक्टर स्पेस होगा. ऐसा क्यों? क्योंकि हमारे पास रिलेशन क्या है, एक दूसरे पर कंटेन कर रहा है ना?
Yes,
ठीक है?
sir.
कोई डाउट?
No,
अगर
sir.
ये रिलेशन नहीं होता तब हम नहीं कह पाते कि यूनियन वेक्टर स्पेस है. So it is because we have this kind of relation. Okay, this is a vector space. Hence is the chain. So this means we have this. Now as we define G to G head, so this is well defined. How? So this means if you take any element in subspace, say X in DG1 intersection DG2, its image under G head would be unique. So this is the meaning of well defined. हर एक पॉइंट की जो इमेज है वो यूनिक होनी चाहिए, दो इमेजेस नहीं होनी चाहिए. ठीक है? तो इफ से X comes from DG1 and DG2. So as we define G head of X is, यहाँ पर हमने define किया था, for any G in C, G head when we restrict it DG we will get G. So G head of X would be G1 of X and it would be G2 of X. Correct?
इंटरसेक्शन क्यों ले रहे हैं सर?
इंटरसेक्शन क्यों ले रहे हैं
हाँ
सर?
देखो, कोई भी x जो है किसी एलिमेंट dg1 में होगा तो वो आपको पता है कि वो dg2 में हो सकता है ना। वो इसलिए ले रहे हैं कि जब हम किसी एक ही डोमेन से लेंगे तो कोई दिक्कत नहीं, हमने जी हेड डिफाइन किया हुआ है। अगर जी हेड अगर मेरा जी एक्स dg1 से आता तो मैंने जी हेड ऑफ एक्स डिफाइन किया था कैसे?
D of G1
This means g head of x equal to g1 of x. अब मेरे पास एलिमेंट है जो दो सबस्पेसेस से आ रहा है, ठीक है? एक सबस्पेस ये है, और क्योंकि मैं इस तरह के यहाँ पर ये मेरा एक सबस्पेस है, दूसरा वाला सबस्पेस कोई 2 डायमेंशनल थिंग होगा जो, और मैं एक पॉइंट यहाँ पर से उठता हूँ, तो ये पॉइंट इस वाले सबस्पेस में भी है और ये बड़े वाले सबस्पेस में भी है, ठीक है? तो इसका मतलब मेरे पास दो ऑप्शन है जी डैश को डिफाइन करने के, जी डैश एक्स को डिफाइन करने के। एक है जब मैं dg1 से इसको ले रहा हूँ एज ए पॉइंट फ्रॉम dg1, सेकेंड है जब मैं इसको dg2 से ले रहा हूँ, ठीक है? अगर ये वेल डिफाइंड होगा तो दोनों सेम होना चाहिए। जी हेड अगर वेल डिफाइंड हो तो x की इमेज यूनिक होनी चाहिए, और यहाँ पर हमने लिखा है कि जी हेड x g1 x है जब x dg1 में आ रहा है, जब x dg2 में है तो जी हेड x g2 है, g2x, correct? So let's see whether these two are equal or not, g1 equal to g2 or not. So you know, since C is a chain, this means g1 is less than equal to g2 or g2 is less than equal to g1.
so D0
Correct?
is
So this means g1 of x equal to g2 of x. यहाँ से g2 of x equal to g1 of x. ये दोनों ये चीज दे रहे हैं, ठीक है? So this means g1 x equal to g2 x. This means g head x equal to g1 x. Whatever you will take, they will be same. This implies g head is well defined. So image is unique.
yes sir.
And this g head, this is an upper bound. This is an upper bound. So why? Because you take any g in C, g is always less than equal to g head. Correct? This C was arbitrarily chosen, was arbitrary. So from John's lemma, E has a maximal element. Then from John's lemma, E has a maximal element. Say that is F tilde. Okay? And clearly, by definition of E, F tilde is a maximal element, F tilde belongs to E. This means F tilde is an extension of F. F tilde is an extension of F, and F tilde x is less than equal to Px for all x in D of x. Correct? So, I'll stop here. It's not yet completed, so this is not true. It's not yet completed. कैसे हटेगा? Okay, so we will meet on Monday.
yes sir.
And we will complete this proof. अच्छा, Monday छुट्टी तो नहीं है?
होली से होली है।
तो होली के दिन पढ़ोगे?
तो होली के दिन पढ़ेंगे कैसे सर? कलर डाल देंगे हमारे सेल फोन पे सब लोग।
अच्छा ठीक है। ओके, हैप्पी होली टू एवरीवन। मीट ऑन ट्यूसडे।
सर
ओके,
Same to us.